Hello and welcome to E233. I'm your instructor, Gregory Myers. In this video, we're going to take another look at our P5 modified, which is an older version of our P5 modified that focuses on the physics demo. This video assumes a number of things that you have watched the earlier videos focusing on the P5 modified setup, and particularly how I dealt with the projectile 1D version 4 modified, where I passed by reference a structure that inside the structure included singular values as well as parallel arrays. This project is very similar in concept to our original P5, with the difference being that instead of passing multiple parallel arrays, we are passing a singular structure by reference, and then we're reaching into that structure and modifying the individual fields. So you'll notice here that I have already created a projectile 1D results structure. The fields of that structure should look very similar to the functional input arguments for our earlier V4 in our P5 that was not modified. In other words, you should recognize where we had passed our V init, our theta, and then we expected to be updated a time vector, a y time vector, a vy time vector, x time vector, and a vx time vector. And then ultimately the n simply kept track of how many active elements were in each one of the arrays. Now we have to make this distinction here because right now we're creating these arrays much larger than they need to be potentially. We're essentially using n max as a constant to create these static arrays. If the user only wants 11 elements, for instance, in the array, and we have declared them to have 100 elements in them, fundamentally what we have is 89 unused elements. So this is basically a very inefficient process, but we'll focus on how to fix that in a later series. For right now, what we're going to do is we're going to pass this entire structure to our function, and particularly our function 2D V4 modified. And you'll notice that it accepts the address of a projectile 2D results structure. So let's go ahead and jump into the code. I've already done it for us. I would encourage you, rather than just to simply try to look at my code and type exactly what I have, that you instead try to do this yourself first and then just simply use this video as a reference, or perhaps making sure that you've gotten it correct. So just like in our earlier version, I've went ahead and created a bunch of local variables that we are going to need, our t init, t final, t delta, and so on, as well as a y init, x init, to be able to do our calculations for the position in both x and y direction, as well as calculating the initial velocity in the x and y direction based off of our theta and v init. Also, I have my flag or my results variable that tells me whether I was successful or if I failed. And then we initialize some of our values and then jump straight into some of the validation. Once again, like the earlier video with the 1D/4 modified, or excuse me, 1D version 4 modified, we have to prefix each of the variables by the structure, or rather by the name of the structure. And we use the dash greater than sign to indicate that we want the value at that location in the structure. And so we're going to do all the same validation that we did in our P5, make sure that you understand that. For instance, that our v init for our scenario has to be greater than 0. The theta has to be between 0 and pi, and so on, as well as making sure that each one of the arrays are in fact not null. This is not a scenario that we are going to likely encounter, so I wouldn't worry too much about it if you don't completely understand what's going on here yet. But what we want to do is we also want to make sure that our n falls somewhere between 2 and n max, including the values of 2 and n max. If any of those conditions fail to be met, we simply return exit failure. At that point, then we jump straight into the calculations. And this should look vaguely familiar. As a matter of fact, if you simply remove the example with the dash and the greater than sign, it should look exactly like your P5. The only difference being is instead of using individual variables or individual arrays, we are going to reference the elements inside the structure. And so for instance, our y-init that was stored in, our v-init rather, that was stored inside our example structure is now used to calculate our vx-init, the y-init, as well as the theta. You continue this pattern where everywhere that you had otherwise used an individual argument in the function in the earlier version of this project, you simply prefix it by the structure name. Think of it as you were reaching into the structure to get the values out of the structure. Likewise, you can do the same thing when it comes time to assign the values, and that you simply prefix the structure name in front of the fields in the structure. Now, these fields can be individual values, as you saw with our n, with our v-init, and with our theta, or they can once again be parallel arrays. And this is what we are encountering here, is that we have our time array, our y time array, and our vy time array, as well as our x time and our vx time, all are arrays that reside inside the example structure, and we can reach in and we can change individual elements of those arrays. So the process should look vaguely familiar. If anything, it should be pretty comforting to you to see that we're not changing a whole lot. We're just improving on our function signature. In other words, there's not multiple arguments being passed. So I encourage you to go ahead and make sure that you've got this working. As a matter of fact, now would be a great time to go ahead and build it. And then what you want to do is you want to jump back up to main. And particularly what you want to do is you want to start up here with your variable declarations. And you'll note that what I have done here is I have went ahead and created another variable, this time of type projectile 2D results, as opposed to the earlier video where we were focusing on our 1D results, and just simply called it projectile underscore 2D underscore example. We could not have gotten away with reusing the example variable because of the different types. Now, at this point, basically what we're going to do is we're going to update some of the fields inside of this structure before we pass it to our function. And to see that, we simply go down to our /2D/interactive branch, and all of our prompts stay exactly the same as our earlier projects, including collecting the velocity, the angle, and the number of points. But what we're going to do is we're going to load them into our structure. In other words, we're going to assign these values that are in these variables to their corresponding fields inside the structure. Now, later on, we're actually going to see a way in which we don't even have to use these local variables, the n, v-init, and theta. So don't get too tied up on the names matching. They don't have to match. Instead, though, what we're going to do is we're going to pass then the address of this entire structure to our function. And assuming that we get successful results, in other words, none of our validation failed, then we should be ready to print out our table. Now, I've cheated a little bit in this, and I would encourage you to do the same thing. I simply went over to my P5 and I copied and pasted this entire table. What I then did is I very carefully prefixed each one of the fields with the name of the structure. So in other words, what was previously time square brackets 0, or the 0th index in my time vector, now simply becomes the time vector that resides inside of the structure. Once again, we are reaching into the structure to access a specific field. And in this particular case, the field itself is an array. Now, I could have done the same thing here with my v-init and my theta, but I opted just to go ahead and use the local variables. You could simply just go ahead and prefix these as well. 1 second here. So if I very carefully copy and paste this, get an opportunity then to validate that you did correctly assign each one of these fields. And then we'll go ahead and build it. And you once again see that we have working code. Hopefully this little difference here, you can start to understand how we're going to leverage the structure. Now, going through this, once again, we have our time. The 0th element of our time is essentially our t init. The n-1 element of our time is our t final because there are n elements in our structure, or rather in our arrays inside our structure. And so we can once again use the n, or what we can do is we can simply then prefix each one of our n's with the name of the structure. And now you can see here that I am using the n inside of the structure then to indicate the next, or rather the last useful element in our array. And once again, we'll build it just to make sure that we have not introduced any bugs. And at this point, we are done with our table and we can move on to the output to the file. You'll notice that the output to the file, which was described in our P5 modified, was n number of rows. For this particular example, was going to be 6 columns with the index and the time followed by the position and the velocity. The first column was going to be %d. The following 5 columns were going to be %8.4f. Once again, I simply borrowed the code from my P5 and I prefixed it with projectile_2D_example. We can go ahead and build this, and it's probably a good time to go ahead and test this. So if you come along to your P5 modified folder, we'll run our P5 modified.exe. We'll pass it, in this case, /2D switch /interactive. It prompts us for the initial velocity, the angle 0.7854 in radians, and then the number of points that I'm going to put in is 21. You'll see that we have a table here that we could arguably tweak a little bit as far as the format. If anything, I've accidentally put in number, probably go ahead and modify this and just align it. We can play around with the alignment a little bit. But then fundamentally, though, you have your table. That gives you all of your information back, as well as a file called projectile_2D version 4. And in that file are the same results that you would have gotten if you had ran the earlier version, the unmodified. So really what has changed is the structure and how we access or store our data. From the user's perspective, absolutely nothing has changed. At this point, then, you probably just want to very carefully copy and paste these, or rather this code, into the parametric branch. Now, I've made a couple of changes, so I'm going to go ahead and overwrite what I had earlier, nothing significant. Basically just tweaked my table and then modified how I accessed some of the values. And then once again, we can come over here. We can delete this file. We can run this now in parametric mode, providing the additional arguments on the command line. And I'm going to change to a different value here just so you can see. And I seem to have a problem here. Please provide a positive initial velocity. All right, so let's go see what our error is here. Did I accidentally overwrite? Yes, I accidentally overwrote too much. My apologies here. Let's do Control Z. You'll notice that I accidentally overwrote my arguments here. And there we go. And so you must include the collection of the command line arguments. Basically, what was happening there is I was passing the uninitialized values to the function, and essentially they were garbage. Here we go. And now you can see that we have the same results that we would have gotten if we had ran it interactively. So I guess you could say here moral to this particular example is be careful with your copy and paste if you are going to do copy and paste, or you can simply just retype the code. The key is, in this particular example, I had accidentally overwritten my collection of my arguments from the command line. So as always, hopefully you found this video useful. If you have any questions, comments, or concerns, don't hesitate to reach out to me. And thank you for watching.